Hello. I wanted to make a screencast of these graphing things to do, mainly so that if students are absent or if you want to refer back to it, you can do that. So normally I'll make a PDF as well as a quick video for things we do, like homework solutions, things like that. So I went over this Wednesday, August 26th in my Block 1 class. We'll do that Friday, August 28th in my Block 4 class. So first of all, we want to have a relevant title. Normally it's y-axis versus x-axis variables. Okay, so like bounce height versus drop height for one of the things in this lab. We're going to label each axis with units. So with the dependent variable going on the vertical or y-axis, the independent variable going on the horizontal or x-axis. Sometimes that's a little tough to know. It depends on what. It's easiest, I think, to think about what depends on the other thing. So in other words, when you change something, you decide to change something, that is kind of your independent thought. So that tends to be on the x-axis variable as the independent variable. And what responds to that, or what changes because of your actions, tends to be the dependent variable on the y-axis. Do me a favor, when you have when you make a graph, use consistent scaling on each axis. It doesn't have to be the same on each axis, but it should be consistent throughout, so we don't have any breaks in our graphs. So go up by 1s, 2s, 5s, or 10s, things like that. Don't go up by weird numbers like 3, 7, 13s to fill up the graph. Basically, you want your biggest number to be up about 3/4 of the way. 2/3 to 3/4 is fine. You want it to fill at least half of each axis, but not have any numbers off the graphs. Okay. For now, early in the year, we'll start our graphs at the origin, so that's 0, 0 on the lower left-hand side. Please make sure you make your graph easy to read. So you definitely don't need to label each line. That gets super crowded and hard to see. You want to plot your points, so make those pretty big. You're going to want to make a line or curve of best fit. If you use a line, I would recommend using a straight edge like a ruler. We do that to show the trend. So we do not connect the dots because that involves looking at things like some experimental uncertainty, errors, things like that, whereas the trend line shows the best fit, and the whole point of a graph is to convey a possible relationship quickly and make it easy to understand. So if you do have a line, we're going to calculate the slope of that line by picking 2 points, and the point should be from the line, not just data points. That's actually really quite important. So that means if you are making graphs by hand in a group, each group member may have, and probably will have, slightly different slopes. So you shouldn't just have the same slope as your neighbor if your graph is a little bit different. So we get the slope by choosing a point 1 and point 2 and taking the y-axis variable or value of point 2, subtracting point 1, and divided that by taking the x-axis value of 0.2 and subtracting that from the x-axis value of 0.1. I like to show the points I use for getting the slope by putting like a big X on the graph. It's perfectly fine to use 0, 0. The line trends through 0, 0. So I noted that here. I also think it's best to get the slope of a line by using a pretty big stretch of it. But if you notice, I picked something that hit a corner. It's a little harder for me if it's going in between things to try to estimate. So again, your slope can have a little bit of a range to it. But I don't want to pick a tiny area like this, because your slope, if your line is a little bit off, it kind of amplifies that mistake here. Whereas if you take a big area or a big range to get your slope, it tends to minimize any errors or uncertainties. You may need to linearize the graph. We'll talk about that later when we start using graphical analysis, which is a program we'll use. For a graph with a straight line, use your calculated slope to come up with a mathematical model in the form of a y equals mx plus b equation. But that's a math equation. We're going to very rarely, in fact never, I think, compare y's and x's. We're comparing different things. So in the example below, for example, I'm comparing the amount of gas used with the amount of miles driven. So I don't want to see m's, x's, b's, stuff like that. I want to see an equation with your variables. So here's a sample data set comparing miles traveled compared to gallons of gas used. it seems to make sense that the amount of gas used depends on the number of miles you drive. So you choose how long you drive for whatever trip, and the gas used depends on how far you drive. So I've got the data here. I plotted it out, if you notice. These aren't all exactly the same, but it makes sense. Different trips have different gas mileages, depending whether it's city, highway, or whatever. So I made a line of best fit. Notice it doesn't have to touch all the dots. Some dots are above, some dots are close to the line, and some dots are below. So when I do that, I'm going to get the slope. So I choose these 2 points. I have 13 gallons here, 0 gallons here. So 13 minus 0 gallons are my 2 y-axis values. And then 260 minus 0 miles are my 2 x-axis values. 260 down here, 0 right here. So unfortunately this got cut off, which is annoying. So that ends up being a slope of 0.05 gallons for every 1 mile. And I didn't have room to do the equation here, so I did that back above. So the slope sort of means something. It tells us the rate at which we use gas. We don't typically use those units in the US. And Canada and other countries that use liters for gasoline, they do. They have things like 5 liters per 100 kilometers. So they do look at it that way. But we tend to think of it as miles for every gallon of gas. So in this particular case, that would be the reciprocal of the slope, which would actually be 20 miles per gallon. So 0.5 over 1 is the reciprocal of 1 over 0.5, which is the same as 20 miles for every 1 gallon. At any rate, using this slope and this general idea, I started off with G. That's the y-axis variable. That's gas used. My slope was 0.05 gallons per mile. I figured that out down here. And the x-axis variable is amount driven. I put D for amount for driven, and that's the x-axis variable, and my y-intercept was 0 gallons. So the idea here is if I could put in any amount of miles that I drive, I should be able to predict how much gas I'm going to use. If I put in 100 miles, 100 times 0.05 means I'm going to use 5 gallons. If I put in 500 miles, 500 times 0.05, I'm going to use 25 gallons. So that's an example, and in the lab we're going to be collecting some data and graphing some other things. So hopefully that helps.